Okay, it's good now.
Okay. All right. So we started talking about a derivative, an instantaneous rate of change. We even represented, we drew a curve up on the board, and we started talking about the slope of that curve. Well, the curve itself doesn't have a slope, okay? But at each spot along the curve, you could find that instantaneous rate of change, or the slope right at that given point, okay? And that's one of the big things that we will do this first semester here in calculus, is find the instantaneous rate of change, or the slope at a given point. So with that, I'm going to use this diagram here and show you how we're going to find the formula to find the derivative of a given function, okay? So I would like you to, I think this is 1.2, but I don't know, all right? I'll go look, don't write that down.
Okay.
Let's draw this picture, okay? Make it fairly large, all right? We got our x and y axis here. We got our x and y axis. Draw a decent curve, got a little bit of space between there. Put a couple points on it. But again, don't make this too tiny because we got a lot of writing to do in this diagram here.
Everything I do it big.
Oh.
I'm sorry,
We're not calling this curve anything specifically, any specific function, all right? We'll just call it f of x. It could represent about any function. Okay? This first coordinate that I kind of highlighted on that curve, okay? Let's say the x value of that coordinate is simply x. Well, in that case then, the coordinate itself would be x, comma, whatever f of x is. Okay? The coordinate right here, if this is x, the coordinate itself, x comma y, all right,
Which
if you
y
will.
is usually f of x.
We could call that coordinate x comma f of x. Okay, I'm trying to get you used to a little bit of notation here, okay?
So if the next point is 5, then wouldn't it be 5f of 5?
Yes.
Okay.
Correct. Yep, if you're thinking numbers. All right? Let's say the distance from here to here. Okay? Let's call that distance h. Okay?
So it would be x plus h of f of x plus h?
Yes, I believe that heard you correctly. Okay? So if this is x units long, this is h units long, then all the way out to here is how far? X plus h. And then this coordinate right here would be x plus h, comma, whatever f of x plus h would equal. And if you're struggling with that notation, the way I'm writing that up there, please say something now so I don't lose you, okay? Because I can explain it differently a little bit too. Alright? So now what we're going to do is we're going to find the average slope, or the average rate of change from here to here.
Wouldn't that?
Okay? The average. So we're going to find the slope of this line right here. Okay? We're going to find the slope. This is called the secant line. Okay? A secant line. We're going to find the slope of that secant line. Okay? We've talked about our slope formula, right? Okay? So the slope of it would equal what?
f of x plus f of x plus h over 2x plus h, maybe? Unless I did something off.
Careful.
Did I get them flipped again?
X plus h over x minus x plus h.
So if you're doing y1 minus y2 over x1 minus x2, I'm going to switch it around. I'm going to do this one minus this one. Okay?
Okay.
So
Oh,
f
that's
of
what I
x
did
plus
wrong.
h minus f of x over x plus h minus x.
So over 8.
So really just over h. So you get f of x plus h minus f of x all over h. That would be your slope of the secant line.
That's right, because it's the difference. Whoops.
Any questions on that so far? Okay. Now, remember how I talked about the derivative can represent the slope of the tangent line, or like instantaneous slope. That's what the derivative will help us find when we do the derivative, okay? Just like it'll help us find that instantaneous velocity when we do velocity problem. It's going to help us find instantaneous slopes,
I'm sorry,
Okay.
what do you mean by tangent line again?
okay? This is a secant line because it goes through the curve at two spots,
Okay.
okay? A tangent line, you may remember this problem from
Just goes
advanced
through
math.
one spot?
A tangent to a circle, remember, just touches it at one point. Okay, we had a problem like that late in the year with, I think, I don't know, it might have been just with our equations of circles or our conic sections, maybe.
So sort of like what you were talking about yesterday where the slope of a single point,
Like
like,
slope at a single point,
Okay.
yes. Yep, okay. So what we're gonna do with this picture now, or what you're gonna see me do, and if you wanna draw it again, you certainly can, but I think you'll get the idea, right? Let's say I wanted to find the slope of the tangent line at this point, okay? Let's say I wanted to find the slope of that tangent line, okay? Well, what's the problem? Why can't I find the slope of that tangent line?
you don't
You
know.
only have 1 point, right? You don't have 2 points. It's kind of hard to find the slope when you don't have 2 points. Okay? We found the slope of that red secant line, but that definitely is not the same slope as our green tangent line, correct? Okay, so we're all on the same page here? Okay? Alright, so watch what I'm going to do. What I'm going to do is I'm going to make the h value smaller. This would all remain the same, right? If I made that h value smaller,
Wouldn't
so it'd
it
still
be a
be x
different
plus
h?
h, comma, f of x plus h?
It would
and
just
that-
be a different h.
Okay, yeah, the h is just different. It's smaller than what it was. If h before was 6, now it's 2 or whatever. Okay, or 6/100ths, now it's 2/100ths. I just made it smaller. Okay? Would the slope of this secant line
Be closer, yes.
would the slope of that secant line equal our tangent line?
Not equal, but it
No,
would be closer.
but is it closer?
Yeah.
Okay? So by making that h value smaller, I got closer to my goal of finding the slope of the tangent line. So what if I make it smaller again? What if I make it smaller again? What if I make it smaller again? Kind of like with the whole idea of the car yesterday, where we took the picture of the odometer on smaller time intervals. If we make that h value infinitesimally small.
Like 0.0 with a googolplex of 0 is 1.
Yes. Yep. Okay? If we make that h value really, really small, we're going to get, essentially, okay, the slope of that tangent line. The smaller we make h to many, many decimal places, we would have the slope of that tangent line, which is going to be accurate enough for what we're doing. Okay, you're going to be very, very accurate. So what we say then is, if we make h really, 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 really tiny, then this is actually our slope of the tangent line. But h has to be really, really small. All right? And the way you write that is you write the limit, that's what this stands for, as h approaches 0 of f of x plus h minus f of x all over h. That is your, and I'll just write slope of tangent line, that way you know.
So is this just supposed to be probable in a perfect world, basically? Like, in other words, for our car experiment, if it was a perfect world where it never broke down, never had different things like that, it would be likely that it would stay on this track? Or does that make any sense?
I don't know if I'm quite following
It
you.
wouldn't matter because it's just the tangent line. Not
If
the-
you're talking the car and the instantaneous velocity, yeah, I mean, we're assuming that it's the car was continuously moving, and if we took smaller and smaller and smaller time intervals, we could kind of use this idea of the secant line to find the instantaneous velocity we're going at a very given split second.
Okay.
Okay? So the derivative here, derivative is something we can use to help us find the slope of the tangent line or an instantaneous velocity. Okay? So our derivative, which you'll eventually, we'll talk more about this. The notation we use for a derivative of a function is f prime of x. Alright, we're not into that a lot yet, but that's the notation we will eventually use. The derivative can be found by taking the limit of this function as h approaches 0. So in other words, finding the value of this as h gets really, 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 really small. Okay? What questions do you have on that? What have I not explained clearly? I mean, we're not ready to do one of these yet. Okay. Do you get the idea with the picture, how if I keep shrinking h, we're getting closer and closer and closer to the actual tangent line? Is that making some sense? Okay. That's what derivatives do. Derivatives, which we're going to spend a lot of time doing derivatives this semester, okay? The derivatives will help you find instantaneous velocities, or in a sense, instantaneous slopes, or slopes of tangent lines at a given point. Okay? I want to show you a visual aid with it too. You can probably pause that now if you don't
I
mind.
don't know if you have like